Swayam Prabha. Digital India. Educated India.
So I have an interesting surprise for you today. I've been thinking about this. I'm sure you're missing IIT Bombay quite a lot. And for the people who are watching these videos on satellite transmission, you might be wondering how IIT Bombay students, where do they work and things like that. So this is our really popular well lab, Wadhwani Electronics Laboratory. And you can see these whole bunch of setups here where all the students do their experiments. So I thought it will be great or rather interesting video to show you the lab so you don't feel IITB sick. Today we are going to talk about, start talking about devices, semiconductors and devices using semiconductors. So the first device we're going to talk about is PN junction. So here is I have a PN junction diode that I would like to show you, and if you observe this diode carefully when you're back, or if you have a chance to look up one device, you will see a ring around the device, okay, on one side. And generally whenever you see that ring, so for example in this particular device the ring is on the left side, and that is a cathode of the diode, okay. We have anode and cathode. Anode is the positive terminal, cathode is the negative terminal, and the ring indicates a cathode. Here is another diode that I would like to show you. Now it's a little bit tiny device. Again, in this case also you will see a black ring on one side, and this one is a Zener diode. Okay. So I'm going to explain all these devices to you in this lecture. Generally, there is a companion course going on in every university, which is a deep devices course, where you learn how the devices are manufactured, how is the electrons, holes transport going on in a semiconductor and things like that. And there you learn a lot of equations. In this particular class, I could just start from equations of diodes or bipolar junction transistors, but then I feel that you will probably miss out a lot if I don't give you some intuition. So what we're going to do in this class is we're going to go through intuitive level understanding of these devices, how the transport is happening, electrons, hole transport, majority carrier, minority carrier transport, that's happening. And by that you will be able to recall or remember how these devices work, and then we can get into a circuit level model of the devices, and then we start using those devices in different circuits. Thank you. In today's lecture, I'm going to talk about semiconductors, P-type semiconductor, N-type semiconductors, and then how do we make diodes. Just a few minutes ago I showed you a diode in the lab, and I was trying to describe it to you, and here is a diode that you can buy as a component, and it kind of looks like a cylinder, and then there is this terminal that's coming out of it, okay. And in this particular case, the one when I showed you, it had a white or a silver ring around on one side, and the thing I was trying to tell you was this ring generally denotes a cathode, K or cathode. Terminal, if that is the cathode, then this is the anode. The symbol for the diode is like this, and as I have explained to you, you look from this way, you see a K, and that's your cathode. Cathode denotes negative terminal. And if you look from this, you see an inverted A, that's anode, and that's a positive terminal. And this arrow is showing the direction of the current that it can carry. Now, before we get into the diode, let's talk about silicon as a semiconductor. Now, if you look at silicon as an element, it has 4 valence electrons, okay. So they are in the outermost shell of the atom, And if you add 4 more valence electrons, then it's very happy. You know, all the bonds are complete. So for example, if you have one atom and then somehow it connects with 4 other atoms and shares the electrons with each other, okay, like this. Now you have this is each atom, silicon atom, okay, like this, silicon, each atom, and it connects with it shares its electrons with the neighboring atoms like this, and of course this will continue going on like this, okay. Now these 4 valence electrons are shared with the neighboring atom, as a result of which you form these covalent bonds with the neighboring silicon atom. Now things are all fine like this, and if you just take a silicon, pure silicon as is, then it, you know, at really cold temperature it probably feels like an insulator. There is no current flowing through the silicon. Let's say you take a, you know, blob of silicon, then there will not be any current flowing through it. However, at room temperature, some of these you know, covalent bonds can be broken at room temperature just because of the thermal excitation of the electrons, and they are moving around with the thermal energy, and sometimes they escape the bond, and whenever they escape the bond, the electron becomes free, and wherever there is a absence of electron, we call that as a hole, and holes are positively charged, electrons are obviously negatively charged. As a result of these free electron hole pairs, we have some current that can flow through this silicon at room temperature, and that's why we call it semiconductor. Okay. In a perfect conductor, you will have tons of electrons, and then the current will be carried using those electrons as a transport medium. That's why they are metals, because they have a lot of free electrons. In a semiconductor, at room temperature, some of these you know, covalent bonds can be broken because of the thermal excitation, and then there could be some amount of current that would flow in a semiconductor. Okay, so for example, in this particular case, we are talking about silicon as a semiconductor. So as it is, it's not a very useful, you know, we cannot really use it anywhere just as a semiconductor. The cool thing that happens is when you introduce some impurities in this silicon. So there is one equation that that is useful here, which is for silicon as a semiconductor, is P times N is equal to Ni square, and this Ni is called intrinsic carrier concentration, and the value of Ni is equal to 1.5 10 to the power n per cm cube. So in every cubic centimeter there will be 1.5 into 10 to the power 10 carriers, intrinsic carriers at room temperature. Okay, and P and N happens to be, P will be the hole concentration and N will be the electrons concentration. All right. So by itself, silicon is not, as a semiconductor, is not very interesting, okay, because it has only few carriers which can carry current, and that's why we call it a semiconductor. Now let's say we adulterate this silicon. Okay, I use the word adulterate because we are going to make it impure, intentionally impure, and the element we are going to use is boron. So boron has only 3 electrons in its outer shell. You will have one missing electron in the silicon when you introduce a boron, and boron is called an acceptor impurity. I'm kind of visualizing it for you. You take silicon and you put some boron into it, and the concentration of boron in this silicon is given by Na. Na is equal to some number per cm cube. All right. So in that case, since it's an acceptor impurity, the concentration Na is pretty much equal to the holes, which would be the holes in the semiconductor. Okay, so we call them, holes are denoted by P, and since we are adding boron, it's a P-type material. Also, as I said, this is a P-type material. Okay, P-type semiconductor. Okay, so this P denotes P-type and this P denotes the hole concentration. So in this particular case, you will also have electrons, and electrons will have N sub P. Okay, so these are electrons. Again, these electrons are happening because of thermal excitation, you know. So since we are dominating the silicon piece using acceptor impurities, we can call this as a majority carrier, and this would be your minority carrier. Okay. Similarly, we can talk about donor impurity, where donor impurity, and that would be N-type semiconductor that we will form. In the donor case, we would add phosphorus. Okay, phosphorus has 5 electrons in its outer shell, so we have 1 extra electron. Now, when you dope silicon with phosphorus, okay, then you will have this is called Nd, that's a donor impurity, and that is again given as number in cubic centimeter. Okay, so in this particular case, we would call it N's of N. This would be your Nd, and P of N would be the holes due to thermal recombination in the N-type semiconductor, and they would be, this would be the holes, and they would be the minority carrier. Okay, and Nd would be, the donor elements would be the majority carriers. So why am I telling you all this stuff? So interesting part is, if you look at a P-type semiconductor, okay, the P-type semiconductor will have minority and majority carriers. The majority carrier would be P sub P, along with minority carrier would be N sub P, and multiplication of this is again equal to Ni square, which is the intrinsic carrier concentration. Okay, so in this case we can say that if P sub P is your acceptor impurity, we said this is Na times N's of P is equal to Ni square. So minority carriers in P-type semiconductor, which are electrons, they are equal to Ni square divided by N's of A, which is the concentration, the doping concentration of P-type material. In this case, it's boron. All right. Similarly, we can prove that for N-type semiconductor, we have N's of N times P's of N is equal to Ni square. This one is still the same, intrinsic concentration, which depends on the temperature, and the minority holes carrier concentration is given by Ni square divided by, what is N's of N? That is your phosphorus doping, which we call it donor, Nd. Okay. So now that we got all this together, let's look at what happens when we put a p-type and n-type semiconductor together. And I'm going to show you a grossly exaggerated image, however, to make a visual impact on you. Okay. And then we have this piece of metal connected on one side, and this is piece of metal connected on this side. Okay. And these are our two connections to the element. So this is a p-type semiconductor and this is n-type semiconductor, silicon. Okay. As I said again, this has acceptor impurities and this has donor impurities. So acceptor is boron and this is phosphorus. There are two types of actions which are happening in the semiconductors. The first one I would like to explain it to you is called, let's take an example. Let's say you bought perfume and you opened the perfume bottle and you just sprayed it. What exactly happens when you spray the perfume? So think about it this way: the concentration of the perfume just outside the opening of the bottle, okay, is the highest. Okay. And as soon as you spray it, the perfume molecules, they will diffuse. The key word I'm trying to tell you is the diffusion. Okay. Another example would be, let's say you have a glass of water and you drop some ink in a glass of water. So wherever that ink drop is entering the glass of water, the concentration is really high, and rest of the water does not have anything, any ink molecules, okay, or pigmentations. And in a short amount of time, those ink molecules will diffuse in the water, and eventually it will all, the ink will all completely dissolve in the water, and you will see a consistent color. Okay. So this mechanism is called diffusion. And where the diffusion happens when you have high concentration on one side and then you're going to low concentration. This is when the diffusion happens. So in terms of our semiconductors, the majority carriers, for example, in this particular case, you have holes here in the p-type and electrons in the n-type. They are majority carriers. So they will diffuse across this junction to the other side, and then what happens? Let's draw the picture with different colors so it will be clearer for you. So I'm just going to magnify the interface for you right here, and let's say this is our interface, and we'll put some dots here. So this is the p-type and this is the n-type. Okay, let's use yellow for the p-type will have holes originally, is dominated by holes. I'm just showing them with yellow to begin with, and n-type will have lots of electrons, and let's use a different color here. We will just show them like this. So there is a high concentration of electrons. So as soon as you bring these together, what we expect to happen is diffusion, and because of diffusion, what we will see then is some of these holes, okay, they will cross the barrier, and some of the electrons will cross the barrier like this. Okay, the holes will go to the n-type because the concentration of concentration of holes is very high on the p-type, and the concentration of holes in n-type, which are the minority carriers, is very low. Okay, so we expect something interesting like this will happen. And this particular area around the junction, okay, will not have any carriers. So holes have left, some of the holes at the junction interface have left to the n-type, and probably they got recombined or with electrons and things like that. And similarly, when electrons came back to the p-type, they kind of sat into some of the holes location. Okay, so what we see then is you will see negative charges on this side, because the electrons have arrived here, and on the other side, on the n-type, since we have lost a few electrons, you will see positive charges. Okay, you will see positive charge here. Okay, let's put circles around the charges so that we don't get confused. So this is positively charged, and the left side, which is p-type, will be negatively charged. And just so that nobody gets confused, these are holes, and the magenta, these are electrons. This area, this colored area here, is called depletion region. And since we have this charge buildup here, you will see some kind of, let me rewrite this here. So you have depletion region, which means all the mobile charges are depleted from the interface section, and as a result of depletion region, we have built-in potential because of separation of charges at the junction, and we call that V0. And as soon as there is a potential difference, there will be some kind of electric field over here. Okay. Now, we only talked about so far one method of transport here. Let me erase this. So what was the method of transport over here? We get eye diffusion. Since the charges move from one side to another side, we get current, and the mechanism of movement of charges is diffusion. So we call it eye diffusion. Now this eye diffusion, as I already said, will set up the space charge region or built-in potential with the polarity as shown, and this would give you electric field in this direction, because positive on the right side and negative is on the left side. Okay. As soon as you have electric field, what happens? I don't know if you have ever done it when you were kids. Every time there is rain, a lot of rain, there is water flowing. Let's say you make a paper boat and then you drop the paper boat in flowing water. The paper boat will just get carried away, right? It will carry and it will go through. It will follow the current. In this particular case, our electric field is like that current. Okay, and the paper boat here would be our minority carriers. So minority carriers. And where do these minority carriers come from? As I said again, these minority carriers are thermally generated. Okay, so these thermally generated minority carriers, which are already there in either p-type or n-type, they will start getting affected by the electric field, and they'll start flowing in the opposite direction. This particular method of conduction is called drift. Okay, so we will see something called drift current here, I drift. And as the name suggests, just like our paper boat will drift in a strong current of water, in this particular case, the minority carriers will drift in the existing electric field, which have happened because of these other things. So at equilibrium, we say that I diffusion is equal to I drift. Let's apply some external potential and then see what happens. All right. So the first case we are going to talk about is another second case. The first one was open circuit. So in this case, we would take a semiconductor and then we would apply this is P and this is N. So I am going to apply a battery potential here and I am going to apply negative potential here and positive potential here. So this is negative terminal of the battery, this is the positive terminal of the battery. Let's call this VR. So since we are applying negative potential to positive node of the or p-type material, we call this a reverse bias. So PN junction under reverse bias. Let's see what happens in this case. So in this case, originally we had this depletion region over here. Let's use a different color. This was our depletion region. Okay. Now by applying opposing potential, we would increase the depletion layer. The depletion region here will increase and the depletion here on the N side also will increase. Okay. And we will have since we have connected positive to the N type, you will have more positive potential on this side. Okay, and similarly we have more negative potential here, something like this. Okay.